Hi, I'm Chem's best friend. If you need any chemistry help, the information how to contact me is on the bottom of your screen. So hello, welcome back. You probably just finished doing electron configurations in your chemistry classes. And it's pretty awesome, isn't it? How the whole periodic table is a big cheat sheet, how to do electron configurations for any element. It's incredible. But the next topic will be trends in periodic table. So let's go to my screen. So when you do trends of periodic table, chances are you will have to be responsible for these 5 trends. And I'm going to say these 3 are very important. And then this one will become important when you talk about covalent bonds and molecules. And in your textbook, you probably have seen something like this. And there's all these arrows going up and down, and you might have to just memorize them. But guess what? I hate just memorizing things. And I don't have any of this memorized. Because what if you just mix one arrow? Then everything falls apart. And it's so easy to do that. So I'm going to teach you how you can figure out any trend of a periodic table, and you don't have to have anything memorized. And if you are in AP chemistry class, you will actually have to explain the trends of periodic table doing things the way I'm going to show you. So many trends, they will ask you to explain using Coulomb's law. So let's talk about what is Coulomb's law. Coulomb's law is very simple, says opposites attract, right? So here is the equation for Coulomb's law, and this is your electrostatic force. Yes, so this is your opposites attract. K is a constant. It will be a positive number. Q1 is charge of your particle 1. Q2 is the charge of particle 2. And D is the distance between particles. So here's the picture. If you do not have absolute value signs, you have to realize that if you have a positive charge here and a negative charge here, you multiply them. This will be negative. Negative will then mean attraction. Sometimes this is shown as absolute value. You have to keep in mind just what you're doing. So if you're not using absolute values, then negative here means attraction. If you have positive value here, that means repulsion. Because if you have positive value, it will be positive here. And if you multiply a negative and a negative value, you will also have a positive value. Just keep that in mind. So Coulomb's law, opposite attract. So all trends can be explained by paying attention to energy levels and E and C. And you say, wait a minute, you just told me about Coulomb's law. So the energy levels, this will be the D, distance, in the Coulomb's law equation. So this will explain energy levels. And this will be talk about effective nuclear charge, will be right there. So we're going to always talk about the energy levels and effective nuclear charge. And you are saying, wait, you just threw effective nuclear charge at me, E and C. What is it? So let's talk about that really fast. What's the definition? So effective nuclear charge, E and C, or sometimes in textbooks written as Z effective, is the charge seen by the outermost electron. So the outermost electron is looking in to the nucleus. Remember, they attracted to the nucleus. And the question is, how many protons does it see? So the equation is this way. So Z effective is Z, which is your number of protons, minus your core electrons. And then now this explains where does Z come from. And if you remember way back when we talked about isotopes, the symbol for isotopes was kind of like this. And we had our atomic number was written as Z. And this is your number of protons. So this Z is this Z, number of protons, and this is called Z effective. It's as if it sees how many protons. So I'll show you how to do that. So are you ready to do our first trend of a periodic table? So the first trend we will talk about is atomic size, size of atoms. And if you look at this trend, you can clearly see, wait a minute, as you go down, any column, any family, yes, as you go down, the size of atoms increases. And as you go across a period, if you go from left to right, the size of an atom decreases. So right here we have our biggest atoms, and then right here we have our smallest atoms. All right, so how do we explain why? And I'm going to pick 3 atoms to show. So any trend has to be explained left to right and up and down. Any trend has to be explained that, yes? So I'm going to pick these 3 elements, sodium, magnesium, and potassium. And this way I can explain left to right trend and up and down trend. All right, you ready? Let's go. So let's explain why. So we have sodium, magnesium. So we're going to start with our electron configuration, which we just learned how to do. So I'm going to quickly write where for sodium is 1s2, 2s2, 2p6, and then I have 3s1. I'm looking at my periodic table next to me. Magnesium 1s2, 2s2, 2p6, 3s2. And then for potassium, I'm going to quickly, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, so now we're going to draw a picture. So we're going to draw, here is our nucleus of sodium, and it has 11 protons, 11 plus. And then I'm going to see, okay, I have first energy layer, I have 2 energy layers, I'm going to draw 3 energy layers. So I'm going to draw 1, 2, 3. Now, you're going to imagine that these go all around, but there's no reason for me to draw this all around picture, but you're going to imagine this is my 3 energy layers. All right, and I'm going to write my electrons on it. So let's write my electrons. My first energy layer has 2 electrons, yes? 2 electrons, right there, 2 electrons. Second energy layer has, well, 2 plus 6. So second energy layer has 8 electrons. And then a third energy layer has that 1 electron, yes? Right there, third energy layer, 1 electron. And then what's happening is this last electron is looking in. Yes, last electron is looking in. And it is as if it sees what? So let's make this a little bit light pink. So this last electron is looking in. What does it see? So we're talking about our ENC. Well, each electron, there's 8 plus 2, 10 electrons getting in a way. And we're going to see that each electron's getting in a way will block 1 proton. So there's 11 protons, but then there's 10 electrons in a way. So 10 electrons block 10 protons, right? So it is as if it is seeing, the last electron is seeing 1 proton. Yes, so number also, if you look at a definition, number of protons minus your core electron. So 11 minus 10, ENC is plus 1. Let's keep going. Let's draw the same picture for magnesium. So magnesium has 12 protons in the nucleus. Here is magnesium nucleus. And I also am going to write 3 energy layers, 1, 2, 3. And on the first energy layer, I have 2 electrons. On the second energy layer, I have 8 electrons. And on the third energy layer, I have 2 electrons. And I drew them separately. And the question is, last electrons looking in. It's as if they see what? Now, keep in mind, the electrons next to each other do not block the view. So the electrons are here, do not block. I can pick any electron and looking in. So ENC, well, let's think about it. What is it? I have 12 protons, but 10 electrons getting in the way. So 10 electrons are blocking 10 protons. So it is as if the last electron saw 2 protons. ENC is plus 2. Okay, so now let's think about how will this help me explain what is bigger going left to right. Well, number 1 is both sodium and magnesium have 3 energy layers. So 3 energy layers, they both the same. This is not helping me. So the D part of that equation, if we scroll quickly up, the D part of that equation is not going to help me. So this is the same, really. This is not changing. It's this is the ENC will help me explain. So let's go back to that. There we go. So the ENC is different. We have ENC1 and ENC2. Now, here is where it gets interesting. You will make sense. If I offer you one candy, or I offer you two candies, which one will you do? You will grab two candies. Hey, I'm getting two, right? So the thing is that the last electron is looking in, and here it sees two protons. Two protons is more attractive to the last electron than one proton. So if two protons are more attractive, these electrons will want to move in closer to the nucleus. They will move closer. So the higher the ENC, the more attraction to the nucleus. And that means they are moving in closer. So the smaller the atom. All right? So energy layers don't help us here. However, ENC, higher ENC, more attraction, smaller atom. Magnesium is smaller. Is it smaller? Let's look. Here it is. You can clearly see magnesium is smaller. All right. So let's go quickly to our potassium. Where potassium, we're going to look here. We have 19 protons. And then I'm going to write 4 energy layers. 1, 2, 3, 4. And the first energy layer has 2 electrons. The second one has 8 electrons. The third one has 8 electrons. And the last one has last electron. So it's my last electron looking in, right? So ENC. So I have 8 plus 2 is 10 plus 8, 18. So 19 minus 18. 19 minus 18. ENC is plus 1. And if you keep doing this, you will see that in your first column, neutral atoms, ENC will be plus 1. Actually, you will see a pattern. All of these will have ENC of plus 1, plus 2. Remember, transition metals are right here. They are skipped. When we talk about plus 3, plus 4, plus 5, plus 6, plus 7, plus 8, except helium. Just watch out, helium is different. So you can clearly see it's the ENC of a neutral atom is the same as valence electrons. Go try it. You're going to see it will work out. So let's compare sodium and potassium. Well, you say ENC is the same, so that's not helping me. However, potassium has more energy layers. So more energy layers, just like, putting more and more layers, this electron, because they're small layers, has to be farther away. So we can say, aha, so this one actually is the biggest atom, most energy layer, and then this one right here is the smallest, because it has 3 energy layers and highest ENC. So now all the trends, everything can be explained by drawing this picture and talking about energy layers and ENC. All right. Now I'm going to pick 2 more atoms. I'm going to pick in germanium and arsenic. And the reason I'm going to pick in is germanium and arsenic have to go through the D energy layer. So I'm going to show you how to deal with that really fast in case you are getting something like this. So germanium and arsenic, let's go. Let's do that. We write our electron configuration for germanium, and I'm going to do a long way. Why not? Quick review. So we're going to do our 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p12. Okay. Arsenic, let me just kind of make sure we have a separation here. Arsenic is right next to it, so I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p123. All right, so let's do it. Let's draw our picture. And germanium has 32 protons, and I'm going to go up to 4. This is my highest energy layer. So I'm going to do my 1, 2, 3, 4. Oops, let's make this a little nicer. 4, and I'm going to put electrons in. So first energy layer has 2 electrons, second energy layer has 8 electrons, and now we're going to add up all my threes. Third energy layer, where there's 2 and 6, and this is 10. Right? So we're going to quickly say, aha, this one I have 18 electrons, and fourth energy layer has 4 electrons. 1, 2, 3, 4. And now you pick any electron at the end, outermost electron looking in, and we can say, okay, what's my ENC? ENC, well, it's 32 minus 28. Yes, 32 minus my core electrons, 28. So ENC is plus 4. Right? And we said, wait a minute, it is exactly what we said. It's going to be, and it also is the same number of valence electrons. Okay, let's do arsenic really fast. Arsenic is right next to germanium, and it is 33 protons, and again 4 energy layers, 1, 2, 3, 4. And we're going to put in 2 electrons on a first layer, 8 electrons. Okay, what about third energy layer? You're going through the d orbitals, yes, so that means 18 electrons. And the last energy layer has 5, because look at this, here is 4, and then 2 plus 3 is 5 electrons. Let's draw 1, 2, 3, 4, 5. And we're going to do last electron looking in. ENC is what? 33 minus 28 plus 5. So this is higher ENC. Higher ENC means more attraction, yes? So you say, aha, germanium and arsenic both have 4 energy layers. So that does not play into role which one is bigger. However, arsenic has higher ENC, more attraction, that means it is smaller. More attraction means electrons are more attracted to the nucleus, they will move in closer. They will move in closer and you have a smaller atom. All right, so I think you can now explain atomic size, neutral atom size. But as we learned in our electron configuration video, that the whole point, of elements is they want to be like a noble gas. So they're going to gain or lose electrons to have S and P orbitals filled. So we get ions, right? So now we're going to explain our second trend of a periodic table, which is ionic size. So right there, our second trend, we're going to explain ion size. So let's go. And when you look at sizes of ions, something becomes really right away clear. So gray colors, if we look at gray colors, gray is our neutral atoms. So we can see that as we go across a period, that they get smaller, right? And if you just look at gray spheres, if you go down, you can see that they get bigger, exactly what we expect. Now, pink is the cations of the neutral atoms, and then blue is the anions, right? So our non-metals would like to add electrons, and metals want to lose electrons. So we have our cations are pink, anions are blue. And right away a trend jumps out that all cations are smaller. And let's explain why. And then another pattern says anions are larger. Now, if you just compare cations, you can clearly see that they follow the trend of neutral atoms, meaning just pink spheres, just look at pink, they again get smaller as you go across, and all cations get bigger as you go down. But let's explain why are cations smaller than the neutral atoms. All right, let's do that. And here we have sodium and sodium ion. Well, we're going to write our electron configuration for sodium. So we have 1s2, 2s2, 2p6, 3s1. And sodium ion, well, sodium ion loses that 1 electron. So we have 1s2, 2s2, 2p6, right? We're going to draw our picture. We have 11 protons, 3 energy layers, and we're going to say 2 electrons, 8 electrons, last more electron, and we're going to pick in E and C, the last electron. What does it see? Well, it sees 11 protons, but then there's 10 electrons blocking. Yes, 11 minus 10, it's as if seeing +1. And this one, sodium ion, 11 protons, but only 2 energy layers. And I'm putting 2 electrons here, 8 electrons here, and the last layer is here, last electrons looking in, E and C is, I look, and it's 11 minus 2, right? +9. Whoa! So you say, wow, not only does sodium ion have less energy layers, so right away it's pointing that it's smaller, but also when you lose that energy layer, the second energy layer now becomes my outermost energy layer, and that means E and C jumps up. So E and C is so much higher. That means so much more attraction. These electrons much attracted to the nucleus. They move in closer, much smaller. So now cations are much smaller than the neutral atoms because many times they shed the outermost energy layer. All right, is this making sense? And we can squeeze in, you know what, why won't we quickly squeeze in a Mg2+, and it's the same story. Mg2+, we have 1s2, 2s2, 2p6, and in case you draw that, you will have 12 plus, 1, 2, and you have 2 electrons, 8 electrons, last electrons looking in, E and C is +10, so this is higher. So magnesium ion is smaller than sodium ion, and here it is. You can see magnesium ion is smaller than sodium. So you can explain the trends between ions just the same way you did atomic size. The E and C increases here. E and C increases and the cations get smaller. And actually E and C increases here too, and the blue spheres, the anions, will get smaller because we're getting more protons in a nucleus. And here they will get bigger because of you adding more energy layers. All right, so, but we explained why is cations smaller than neutral atoms. Let's explain why are anions bigger than neutral atoms. So let's pick the simpler one, fluorine and fluoride. So fluorine atom and fluoride ion. So we're going to have 1s2, 2s2, 2p5, 1s2, 2s2, 2p6. Okay, fluorine, 9 protons, 2 energy layers, and 2 electrons, 7 electrons looking in, yes, and then the last ones looking in, E and C is +7. This is exactly what we would expect. And then fluoride ion, again 9 protons, 2 energy layers, we have 2 electrons, and now 8 electrons on the outermost, last electrons looking in, E and C is also +7. And you say, wait a minute, did we mess up somewhere? So we have same number of energy layers and same E and C. So how do we know that the anion is bigger? Okay, so now we have to use some common sense. We are putting in the electrons onto the same energy layer. So we're putting more and more electrons in. Here we had 7 electrons, here we have 8 electrons. And remember, electrons repel. Same charges, they will repel one another. It's kind of like if you walked up to me, we will feel comfortable standing arm length apart. That's my personal space. If you invade my personal space, I would take a step back, kind of like, whoa, that's my personal space. Well, electrons, they like to have their personal space. So the more electrons you put in onto the same layer, they each take a step back and say, whoa, I want my personal space. So when they take the step back, guess what happens? They have to move away, And for that reason, because electrons repel and you're putting more and more electrons onto same energy layer, the anions are bigger. So you have to use some real common sense to explain. Okay, I hope it's making sense. So we went over atomic size and we went over ionic size. Now we have to tackle ionization energy, electron affinity, and electronegativity. But that will be a longer video, and I don't want to do that. So let's take a break right now. And then, if you want to go over ionization energy, there will be another video for that. So thanks for watching, and see you next time.